Hello, Dan here from howtomechatronics.com, and in this video I will show you how I built this double-barrel Nerf minigun turret for the 3D printed tank that I built in one of my previous videos. Spoiler alert, the minigun or the Gatling gun is actually fake, but it makes this tank look super cool and fun to play with. The turret has a magazine that can hold around 200 Nerf darts, and it can fire all of them in around a minute. That's a firing rate of around 200 darts per minute. The darts can fly at a speed of around 50 meters per second. That provides a distance range of around 12 meters. These are the maximum stats, which aren't something crazy, but we can control them independently, both the firing power and the firing rate, through the RC transmitter. For controlling the tank, I am using a cheap commercial RC transmitter which sends commands to it. At the tank there is a suitable RC receiver which receives the commands and sends them to a microcontroller. The brain of this platform is an Atmega 2560 microcontroller based board or an Arduino Mega board, and for easily connecting everything I made a custom PCB which can be simply attached on top of the board. So, as I already mentioned, we don't have a real minigun or Gatling gun mechanism that fires the Nerf darts, but a simple and common method of firing Nerf darts with the help of flywheels. The flywheels spin at a very high RPM and in opposite direction, so when the soft part of the Nerf dart comes in contact with them, they propel the dart quite vigorously. To get the Nerf darts to that propelling position, we have a rotating part that simply pushes the darts in place as it rotates. And as for storing the Nerf darts, I used yet another simple method. I made a big magazine that holds the Nerf darts, and with the help of gravity and two rollers at the bottom of the magazine, the Nerf darts are brought in place for the pusher to push them into the flywheels. So you see, everything here is so simple. But that simple took me like a month to get this project working. Now I will walk you through the entire process of building this turret and take a look at all design and electronics challenges that I had in order to get it working. That will make this video a bit longer, which might be a bit boring, but I believe that's a good way to learn something new, because we always learn the best from our mistakes, or from others' mistakes, which will be the case for you, because you will learn from my mistakes, but that's others' mistakes for you. Anyway, few words about the tank from the previous video. It's a fully 3D printed tank that I designed, featuring a dual speed gearbox through which we can select a lower or higher gear and get either higher torque or higher speed to suit the terrain or the application that is used for. The tank also has some cool LED lights, that is addressable LED strips through which we can create endless stunning light effects. I made a police lights strobe effect which is so cool driving around with it, especially at night, and especially now in combination with the minigun turret. So for all details about building the tank, you can watch the previous video, and now in this video we will focus on building the minigun turret for it. Let's take a look at the design process first. I used Onshape for designing the turret, which is also the sponsor of this video. Onshape is a professional-grade CAD and PDM system for businesses. Unlike any other professional CAD system, Onshape is built entirely in the cloud, powered by Amazon Web Services. This allows for some really unique features like it enables real-time collaboration, multiple people can access and edit a design at the same time. It runs on any device and you don't need an IT team to implement or update. It tracks all changes and has infinite restore capabilities. You can branch and merge design changes similar to Git. Unlike other CAD software, Onshape never crashes and you never lose your data. These things allow companies to move quickly and focus on their products, rather than managing their CAD system. I highly encourage engineers to sign up for Onshape and get up to 6 months of the professional version for free at onshape.pro www.how-to-mechatronics. Back to topic, now let me show you how I came up with this design. My main goal for this project was to be cool looking, honestly, so that's why I came up with this double barrel design, as well as to have a big magazine to accommodate as much Nerf darts as possible. For the pan and tilt movement of the turret, I used two short NEMA 17 stepper motors. The pan movement happens at the base with the help of a gear set. The base is fixed to the tank and has a fixed gear in the center, and the upper part of the turret pans or rotates as the stepper rotates the other pair of the gear set around the fixed central gear. On the other hand, the tilt movement happens at the back side with the help of a screw drive mechanism. The flywheels are driven by 12,000 RPM DC motors. We need 2 flywheels for each barrel, so we need total of 4 of these 12 volts DC motors. When fired, the Nerf darts fly through the central barrel. The other barrels around it are there just to get that cool looking appearance. For pushing the darts into the flywheels, I am using a 50 RPM DC motor that drives a 6mm shaft through a gear set. On each side of the shaft, we have this darts pusher part, which pushes the darts into the flywheels as the shaft rotates. Then we have this magazine that can hold around 200 darts, and at the bottom of it, these rollers which help guiding the darts into position to be pushed to the flywheels. The rollers are driven by a 20 RPM DC motor paired with a couple of gears to get them rotating in the right direction. This was actually the most challenging part of the entire project. I mean, at first sight it looks simple. Under the gravity the darts should go down and the rollers guide them, but the problem is that the Nerf darts are very lightweight. In addition to that, they are nose heavy because of the front rubber tip, and that makes them so hard to be guided in this way. In order to get this setup working, I went through so many prototypes. Here's the first prototype that I made to check whether my idea for fitting the darts with the help of gravity and rollers would work. Of course, it didn't work initially, but it looked like it might work if I changed the shape of the magazine and the rollers appropriately. You see here the darts arranged in an arc and the roller became pointless. So I added one more roller in order to avoid the arc formation, and now the results were much more promising. In the third prototype, I needed to see how I will further guide the darts in place ready to be pushed to the flywheels. Now the result was worse because, like I said, the darts are very lightweight and nose heavy, so they don't roll quite well down the guided path. Anyway, next I added the DC motors to the flywheels to see how they will work. Of course, the first try was a failure again. The flywheels didn't have the right position to pull the darts well, and also the profile of the flywheels was too sharp and narrow. So I increased the width and made the edges more round. Now they worked much better. In the next iteration, I thought that I should upgrade the output barrel in order to provide better guide for the darts. Instead of just a normal cylinder, I made it profiled to go all the way back to the center of the flywheels. I was making fine progress, I think. At 12 volts, full speed, the Nerf darts were propelled quite strongly. Next, I needed something to push the darts into the flywheels. So I added this part which, as it rotates, it pushes the darts into the flywheels. Simple but quite effective. I connected the DC motor to power and it seemed like it worked. Though this DC motor was around 1300 RPM, which was way too fast for this application. You see, the darts doesn't have enough time to fall down in place properly and the pusher is already pushing the darts, causing it to jam. I changed it with 50 RPM motor, which was much suitable for this application. Once I did that, I moved on with trying to get the whole setup working. I was struggling to get the fitting mechanism with the rollers to work properly. The darts didn't go in place as I intended, until by a chance I held the magazine at a different angle and the darts went all through. I realized that the darts should come straight down instead of guiding them sideways. This way there is less friction and the darts fall in place easier. So I changed the design of the magazine so that the darts fall straight down to the pusher zone. It looked more promising now, but still not good enough. For example, here we can see the darts get stuck at the back side and also at the front. Therefore, I added the front cover that included a small guide for the darts in case they got pushed too soon to avoid jamming at the front. I also removed some material from the back side in order the darts to fall easier, but still they were getting stuck from time to time. I also increased the pusher diameter so it can better grip and push the darts. Overall, I thought that this prototype worked well enough, so I decided to move on and design the whole turret based upon it. You see, sometimes it takes so much time and effort to get things working. I actually ended up modifying the design few more times even after assembling the turret. You will see that later in the video. Anyway, you can find and download the 3D model of this tank and the turret, as well as the STL files needed for 3D printing on the website article. The link is in the description of the video. I used the Creality K2 Plus 3D printer for printing all of the parts. I always say this in my videos, when 3D printing it's essential to use the horizontal expansion feature, or now in the Creality print slicer it's called XY contour compensation and XY hole compensation. If we leave these settings by default, the print's dimensions probably won't come out exactly the same as in the CAD model, and that's due to the expansion of the filament when 3D printing. The holes usually come out smaller and the contours bigger. For this project, for some of the parts, like for example the magazine rollers and their shafts, we need loose joints or clearance fit. And on the other hand, for some parts, like the barrels assembly, we need tight joints or interference fit. So we either use negative or positive values for these settings, depending on the part that we print. I used values within a range of plus minus 0.1 mm. Though you can only get these values right by doing some test prints with different values. By the way, shout out to Creality for providing me this excellent 3D printer. The Creality K2 Plus is one of the best 3D printers I have ever used. You can simply throw anything at it, whether it's a small part or as big as 350 by 350 mm, and it will get the job done perfectly. It's capable of doing anything you would ever need from a 3D printer. It has an outstanding print quality, it's fast, it can print any material with ease, it can print multicolor, and it has a ton of cool and practical features. You can check out the K2 Plus on the Creality web stores. The links to it are in the description of the video. Alright, so here are all of the 3D printed parts so we can start assembling the turret. It takes quite some time printing everything as there are so many parts and some of them are quite big. You can find a complete list of all components needed for this project, like the DC motors, the bearings, the bolts and nuts and other stuff on the website article. Actually, before assembling the turret, I had to clean the tank a little bit from my previous use, because it was all covered in dirt. I took off the tracks and cleaned them well with a water and a brush. Before putting back the tracks though, I installed new springs to the shock absorbers. This is a must-do step, because now with the turret, we will add quite a mass to the top of the tank. The original springs of the shock absorbers are just too weak and won't be able to hold up all that weight. I bought springs with the same dimension as the original, 30 mm in length and 50 mm outer diameter, just with thicker wire. The original wire was 1 mm thick, and I could easily press that spring with just 2 fingers. The new ones were 1.5 mm thick and were much stronger. At the back side I even installed 1.8 mm spring, because most of the weight of the turret will be at the back side. Though I would recommend you to get just the 1.5 mm springs, as they would be strong enough even for the back. Anyway, we can start the assembly with installing the base of the turret in place. This base part will be fixed to the back side of the tank cover. There are 2 holes on the inside of the base that match with the 2 holes on the tank cover, and we will use them to align the base properly. And using a 3mm drill, make holes to the tank back cover. I specifically placed these holes to be on the ribs on the inside of the cover, so they will be strong enough to hold the turret base securely. I also marked and made a hole for the wires from the turret to pass through. I mean, these new holes will be updated to the original tank 3D model files, so if you are building the tank now, the holes will be there. We secure the turret base to the tank cover using 4 M3 bolts and nuts. Next, we can install the panning platform on top of the base. This platform sits and rotates on top of some ball bearings attached to the base. I'm using bearings with 30mm outer and 6mm inner diameter. My intention was to use bearings with 4mm inner diameter, but I ran out of them, so I 3D printed some sleeves so I can still use these bearings with 6mm inner diameter and M4 bolts. You see, I installed 4 of these bearings, but I will update the model to be with 6 bearings to have better contact. To keep the two parts aligned, we are using a bearing with 47mm outer and 35mm inner diameter. The bearing fit in between both parts, and so we get a nice and smooth motion. For securing the upper part, we will use this flange on top of the bearing. Though before we do that, first we need to insert the stepper motor for the panning. The stepper motor is an IMA 17 but just with 24mm length, so it can fit in place. Maybe we could also go with a 30mm long NIMA 17 motor, because I later found that this shorter one was struggling a bit in terms of power with the pan movement. At this point we also need to attach the gear to the motor shaft. For securing it in place, there is a slot for inserting an M3 bolt, and then using a grab screw we can firmly secure the gear to the shaft. To finish the pan assembly, we need to install some threaded inserts into the base, and then using the flange secure the bearing, and with that the planning platform is secured in place. Next we can install the tilt platform. That's this weird looking part which is like a Swiss cheese. Yeah, it has so many holes because we need to attach so many parts to it. For the tilt joint, we need to install 2 bearings on the sides of the platform. These are the same 13mm outer diameter bearings. It's worth noting here that we should not force insert the bearings into the holes, because the part here is only 5mm in width and could easily delayer or break at this location. I used a diamond file to smooth out and expand the holes so that the bearings can fit easily. Using 2 M4 bolts we secure the tilt platform in place and so form the tilt joint. Next we can install the bracket that will hold the tilt stepper motor. Then we can install the cylinder-like part that will form the drive screw mechanism for the tilt movement. We also need an M4 threaded rod for that purpose. We need 2 pieces of 66mm length. So first goes an M4 nut at the top of the cylinder part, and then we can screw in the threaded rod. For connecting the 5mm stepper motor shaft to the 4mm threaded rod, I will use this 3D printed coupler which can be tightened with an M3 bolt and nut. Then using the other 66mm rod, we just have to connect the stepper bracket and so form the tilt mechanism. So as we rotate the threaded rod, the tilt mechanism goes either up or down. Though we can notice here that the mechanism is not that sturdy. The wobble comes from the M4 nut, which is not tight fit in the cylinder part. I replaced that cylinder to have tighter fit, and now it was better. Of course the whole tilt mechanism wobbles a little bit, because the M4 nut and the threaded rod have a play between them, as well as the other joints, but it's good enough I think. Next we can move on with installing the flywheels DC motors. These are 12,000 RPM 12 volts DC motors. We need M2.5 countersunk bolts to secure them in place. Once secured, we can insert the flywheels to the motor's shafts. The whole of the flywheel is dimensioned and 3D printed with tolerances to make an interference fit with the motor shaft, so we don't have to use any screw for securing them in place. There should be 2.5mm gap between the flywheels and the tilt platform, so here I'm using a 2.5mm drill as a limiter when inserting the flywheels. Though I later noticed that the shaft of the motor has an axial play of around 0.5mm when pressed, so with the 2.5mm drill as a limiter, we got 3mm gap. So we should use the drill or anything else with 2mm as limiter. After installing the flywheels, we should check whether they have good contact with the Nerf darts. They should have a good grip, but at the same time they should not be very tight. For getting the right grip, you can try different values of the horizontal expansion settings when 3D printing. That's also the case for getting the right hose dimensions for the interference fit with the motor shaft. Next, we can install the part that holds the Nerf darts before they are pushed to the flywheels. We secure it in place with two M3 bolts and nuts. I think it's good to have parts like this to be modular or not printed together as one part with the platform, as in this way we can modify them at any time if needed. At this point we can connect the flywheel's DC motor to power to make sure they work properly before we move on with the assembly. We will move on with installing the output barrel now. This part is designed to fit in between the flywheels and to guide the Nerf darts in the center in case they come out of the flywheels at an angle. Before securing it to the tilt platform, we need to insert two bearings with 47mm outer and 35mm inner diameter and with some distance rings between them. These bearings will accommodate the rotating barrels of the turret. Also, we need this retaining ring, which will later hold the rotating barrels mechanism in place. We secure this output barrel to the tilt platform with two M3 bolts and nuts. Next, we can install the barrel base. This part will rotate through the bearings around the output shaft we just put. For securing it in place, first we need to install some threaded inserts to it. Then we can put it onto the bearings. We secure it in place with the retaining ring at the back and with the help of some M3 countersunk bolts. Once we have the two barrels bases in place, we can put the drive gear in the middle in between them. The gear will be driven by a 12 volts DC motor. In my case that's 1300 RPM motor, but it can be as low as 300 RPM. The DC motor is fixed in place with the help of a bracket that is attached to the tilt platform. Using a grab screw we can secure the gear to the motor shaft. Now let's make this turret look super cool. We will assemble the barrels and make it look like a minigun. I chose to have one bigger barrel in the middle, through which the Nerf darts will pass through, and three more smaller barrels around that one for getting that cool visual appearance. For easier printing, I divided the barrels in half. They are not exactly in half, but with a slight difference in length, so we should keep that in mind when assembling. For assembling them, we will use these brackets, which are both functional and add up to that cool looking factor. So we simply insert the barrels into the brackets, but here it is important to have a proper fit between them, so they stay firmly in place. To achieve that, we can play with the already mentioned horizontal expansion setting in your slicer when 3D printing. You should do some test prints first, I guess, in order to find out what values will give you the interference fit. In the first section, the central barrel should be the longer one, while the three other barrels should be the shorter ones. The second bracket should be inserted in the opposite direction, halfway through the output barrels. Then we can add the second set of barrels and the brackets at the end. Here I'm inserting two brackets at the end, again just for better visual appearance. The outside barrels should be flush with the last bracket and the central barrel pulled back a little bit. Lastly, we can simply attach this barrel's subassembly to the barrel base with the help of 3 M3 bolts. We need to repeat the same process for the other side, and so we are done with the barrels. They just look super cool. Even cooler when I powered the motors and they start spinning. However, we can notice that the weight of the two barrels significantly bends the tilt platform. When doing this test, the platform even broke. It was actually really bad designed. A single point of around 8mm was supporting the entire weight in relationship with the tilt joints on the sides. So of course I had to redesign it to make it sturdier. Luckily there was enough room to add more material and increase the strength at that point of the part. I also connected the sides with the central part for some additional strength. These are just small connections with 6x7mm dimension because that was the only available space for that purpose, but still mean a lot for improving the sturdiness of the entire platform. I also increased the number of bolts and the infill density when 3D printing the redesigned part. It feels so much sturdier now. I reassembled everything and tested it again. It was much better, though now the coupler between the stepper motor and the threaded rod failed. That wasn't a big deal though, as I just made the coupler longer in order to tighten it with 2 bolts instead of 1. The tilt mechanism still wobbles after all the added weight, but it doesn't come just from the tilt mechanism, but also from the pan joint, which seemed a little bit loose. That's why I said that I will upgrade the pan base to have 6 supporting bearings instead of 4. Anyhow, we can move on with assembling the Nerf darts pusher mechanism. First, we need to insert the DC motor in place. Here I am inserting a 1030 RPM one, but then I realized that that's way too high speed for that purpose. We need maximum 100 RPM motor here. Anyway, this DC motor, through a gear set, will drive a 6mm shaft to which we will attach the pusher parts on both sides. As a shaft I am using an M6 threaded rod because it's much cheaper and easier to get. Threaded rods are not that accurate compared to a proper 6mm shaft, especially when used in combination with bearings, but that's fine as we don't need much accuracy for this mechanism. The length of the shaft is 166mm and it's secured in place with the help of some M6 nuts in the inner section of the tilt platform, which are tightened against the ball bearings. The gear and the pushers are secured to the shaft with some grab screws. The pusher mechanism seems to work properly now. Alright, so next we can install the magazine for the Nerf darts. But before we do that, it's better to add the wires to the DC motors, as currently we have more access to them. We need like 30cm wires for each motor. As for the flywheels motors, I connected them all together in parallel, so only a single plus and minus wire would go to the controller, as all of them should work at the same speed and be controlled at the same time. Though we should test the polarity to make sure that each flywheel spin in the right direction for firing the Nerf darts. We can also connect the stepper motor and then pass all wires through the central opening. Now we can move on with installing the Nerf darts magazine. This one can hold around 200 darts, but we can easily increase the capacity by simply expanding it up or to the sides. For connecting the tilt platform, we will use these brackets and some M3 bolts. But before we do that, we should install the DC motor for the magazine rollers. That one goes on a bracket that we first need to secure it to the magazine with some M3 bolts. The DC motor I am installing here is 12 volts 50 RPM, but we could also go even lower like 20 RPM. As the rollers will operate at a very low RPM, the shafts for them are just 3D printed. This DC motor will drive the rollers through a set of gears. You see here the left roller is directly driven by the motor's gear, and the right roller is driven by another gear in between the roller and the motor gear in order to produce opposite direction. We need to install some threaded inserts to the magazine and then we can use them for attaching the cover for it at the back side. Now we can insert the magazine in place and secure it to the tilt platform with the brackets and some M3 bolts and nuts. And that's it, our Nerf minigun turret is completed, except for some covers that I will later add for enclosing and protecting the moving parts. Now we can connect the DC motors to power to see how everything works in motion. Now it's also a good time to add some Nerf darts in the magazine to check whether all of this actually works. Once I powered the motors, it fired few Nerf darts, but very quickly got stuck. What happened here is that the pusher was faster relative to the rollers, and it tried to push the darts while not being in the correct position all the way down to the pusher. I unstuck the dart by hand by manually pushing back the pusher, and so the dart took off, followed by a few more, and then it stalled again. It was the same problem. We can notice that in this close-up shot where the darts hit the front of the magazine wall. Actually, I already took this into consideration when doing the prototypes, but I forgot to implement it here. You see here I had this chamfer-like section to guide the darts into the wheel even if it's pushed earlier. Though on the other side, an opposite problem occurred. As the darts are nose heavy and this system works with the help of gravity as well, they sometimes fall faster at the front and the back side of the darts get stuck at the back cover of the magazine. So apparently the loading system didn't work well at the time, so I had to do some tweaking. I tried manually moving the pushers a bit slower than the motor did, and in that way I got all darts fired without getting jammed. The pusher motor was just too fast, so I replaced it with a lower RPM one, just like I said previously. We need around 100 RPM motor at most. Here I am testing it with a lower RPM motor for the pusher, and bingo! It fired all of the Nerf darts without getting stuck. I loaded the magazine with some more darts on both sides now, and again it showed good results firing all of them. Though I noticed that the pusher needs to be a bit bigger so it can grab the darts that move to the back and stay a little higher. I replaced the pushers with bigger ones and did few more testings which showed decent results. I said decent because from time to time the darts would still get stuck. I was trying to figure out what is the main problem now, and I realized that even though I have a roller, the distance between the roller and the opposite wall was greater than the Nerf dart diameter, and so I didn't have a properly controlled guide of the darts. My conclusion for this problem was that I should add another roller so that the darts are guided and controlled to fall one by one through the two rollers. I made a test for this theory, which seemed that it would work well. However, that also meant that I should redesign the whole magazine to make space for that second roller. Luckily, Onshape is quite versatile and I easily managed to make space for it and reshape the magazine appropriately. But now I also needed to modify the gears that drive the rollers. The two rollers' gears had to mesh to each other and in that way create the opposite direction, which was fine, but I had to increase the teeth number because now I had a fixed central distance between them. Using an online calculator for calculating the gear's central distance, I found the suitable number of gears teeth that I needed for the two rollers to have that desired central distance. By changing the roller's teeth count, I also had to change the other gears' teeth count, as well as their location on the bracket so that they can mesh properly. Again, with the help of the calculator and Onshape, that was easy to do. I initially found the approximate number of teeth for the gears that I needed, entered those values in the calculator, which gave me the central distances measurements, and then entered those new values for the distances between the gears in Onshape. With this process, we had to update both the motor and the idler gear location on the bracket. So I reprinted everything again, the bracket, the rollers, the gears and the magazine. This time I made the shafts for the rollers to be separate parts instead of being printed with the magazine. This provides more flexibility if something needs to be modified. We secured them in place with some M3 bolts and threaded inserts. I assembled everything together and it seemed that the rollers are now working as intended. Now at the front face of the magazine I left an opening for the problem that we faced earlier. Also I made these parts that will guide the darts into the flywheels if they are pushed earlier. They are attached in place with an M3 bolt and a nut. Here's the new setup in motion. I also changed the pushers to have 2 sticks instead of 3. Now I thought that's it, the turret will work perfectly. But that wasn't the case. Again, similar problems occurred. The pusher stick was getting stuck into the darts. So I got back the smaller pusher to see how it will perform with it now. It performed better with it, but still not good enough. Now I realized that another problem occurred. We can see here as the rollers push the Nerf darts in place, if not fired on time, the bottom one gets stuck because the rollers produce downforce to it. I had to think of a new solution again, and luckily it was easy one this time. I just had to reduce the diameter of the rollers so that the gap between them is still small enough to hold a dart without falling down uncontrollable, but big enough so that it doesn't push the upper darts that hard on top of the bottom ones, so that the pusher is able to push the darts to the flywheels. That actually solved the problem. Finally, after so many tweakings and updates, the work of the Nerf darts loader is acceptable. I wouldn't say it's like 100% perfect because it still can get stuck from time to time, but still I think it's good enough. Nevertheless, now we can move on with the electronics or connect the turret to the custom PCB that I have on the tank. We need few additional components to get the turret working, and here's the circuit diagram for it. So the 4 DC motors for the flywheels will be controlled through a single MOSFET with a PWM signal, and another MOSFET for the barrels motor. We don't need to change the direction of rotation for these 2 motors, so that's why we are fine with just controlling their speed with the PWM signals. On the other hand, for the rollers and the pusher motor, we will use the dedicated DC motor drives, which also have H bridges, so that we are able to change the direction of rotation. I want to be able to change the rotation direction because in case of getting the darts stuck, we can activate the rollers and the pushers to go in reverse direction and so unstuck the darts. This function turned out that it works. For driving the 2 NEMA 70 stepper motors for the pan and tilt mechanism, we are using 2 A4988 stepper drivers. I pulled out the custom-built PCB from the Arduino Mega board and soldered in place these few additional parts. You see, when I designed this PCB in my previous video, I planned ahead and included dedicated spots for connecting the MOSFETs as well as the A4988 stepper drivers. You can find and download the Gerber file for this PCB from PCBWay project sharing community, through which you can also directly order the PCB. Yes, I ordered the PCB from PCBWay. Here we can simply upload the Gerber file, choose the properties of our PCB and order it at a reasonable price. I didn't change any of the default properties except for the PCB color, which I chose to be blue. PCBWay provides great PCB manufacturing and assembling services, which I highly recommend. But also they are offering CNC machining, 3D printing, sheet metal fabrication and injection molding services. Anyway, we should connect everything as described in the circuit diagram and put back the PCB in place to the Arduino Mega board. Though instead of using the more efficient DRB8871 DC motor drivers for driving the rollers and the pusher motors, I ended up using the outdated and inefficient L298N DC motor driver. I simply couldn't get the motors work with the first drivers. I couldn't control their speed properly with the PWM signal. For powering the tank, previously I used 3S LiPo battery, which was okay, but now I think that a 4S LiPo battery is more appropriate. With the 3S LiPo battery, when the cells voltage dropped to their nominal value, 3.7 volts, the total output is around 11.1 volts, which is already below 12 volts and so we lose power to the motors. With the 4S LiPo battery, the nominal total output is around 14.8 volts, which is actually way above 12 volts, but we can use a buck converter to fix the output to 12 volts. That way we will always get that fixed 12 volts at all time, no matter if the battery is fully charged to 16.8 volts or drained to 14 volts. Though we should make sure first we set the desired voltage of the buck converter before connecting it to the circuit. What's left to do now is to program the microcontroller and give life to the turret as well. I will just quickly go through the Arduino code, and on the website article you will find more details how it works, as well as you will be able to download it. So using the iBus BM library, we read the incoming data from the RC transmitter. We are using all 10 channels on the popular FlySky FSI6RC transmitter. This is officially a 6-channel RC transmitter, but we can turn on 4 more channels to work. We convert the incoming data into suitable values depending on what we are using them for. For example, we convert the left joystick, channel 3 incoming data, into values from 0 to 400, which are then used with the setSpeed function within the Excel stepper library to run the stepper motor with an appropriate speed, left or right of course. On the other hand, for controlling the DC motors, we convert the incoming data into values from 0 to 255 for driving the motors with PWM values using the analog write function. Nevertheless, for more details how the code works, please check the website article. Once we upload the code, we can power up the tank and the RC transmitter and test it out. With the right joystick, we can control the tank movement. I set the lights control to the left 3-way rocker switch so that we can choose 2 different light modes. With the left joystick we control the pan and tilt system of the turret. With the very right joystick we activate the Nerf darts firing. With the right potentiometer we control the firing rate, and with the left potentiometer we control the firing power, that is the flywheel's RPM. The cool part is that everything can work simultaneously. The tank can fire Nerf darts while driving and panning and tilting and having the lights turned on. I loaded up the turret with some Nerf darts once again to test it out. It fired all Nerf darts without any problem, which was so satisfying to watch. Nevertheless, there is actually one more thing that we need to do, and that's to add the covers of the turret so that we hide and protect the moving parts. This is the front cover that goes through the barrels in the front, but to attach it in place first we need to add 2 of these brackets to the tilt platform. Then using 2 M3 bolts we can secure the front cover in place. At the back side we will use this cover to protect the roller's gears. I already printed this cover for the previous version of the magazine, but I managed to put this one by just making 2 holes to it with a drill. Again, using 2 bolts we secure the cover in place. And lastly we can add these small covers that hide the darts pushers. We also have a top cover which can be easily inserted in place with just 2 bolts, as well as it can be easily removed for loading the Nerf darts. And that's it. The turret is now both protected with the covers and it looks cooler. Nevertheless, that was a hell of a ride, to be honest. I faced so many problems when designing and building this project, and that's why I decided to show you all of that, so that you can see what it takes sometimes to make a project like this. Please let me know in the comments what are your thoughts, whether I should keep doing my videos in this format, showing everything in details from how I designed the project to going through every step of the assembly and how I solve challenges along the way, or I should try to make the videos shorter, with less details but show more of the finished work. I hope you enjoyed this video and learned something new. Don't forget to subscribe, and for more tutorials and projects visit howtomechatronics.com.